Hey guys, welcome back to another instruction lesson here with Mr. Gaines as we continue our work with exponential and logarithmic functions. Today we're going to get into a new section of notes which will deal with solving exponential and logarithmic equations. So there's a variety of different techniques we're going to use in solving exponential and logarithmic equations. And the first of these techniques relies on some different properties of logarithms. So we have two fundamental properties of logarithms. The first one is that log base b of b to the x power is equal to x. And this is because b to the x power equals b to the x power. So why is this important? Well, we know that b to the x power is equal to b to the x power. That's the same expression. But what I can do here is I can take this expression and rewrite it as a logarithm. So if I'm going to take this expression and rewrite it as a logarithm, this would be log base b, there's my base, of the output for the exponential function becomes the input for the logarithm, b to the x power, and then the input, the exponent, becomes the output for the logarithm or logarithmic function. So log base b of b to the x equals x. Basically what this is taking b to the x equal to b to the x and rewriting that as a logarithmic expression. The same thing can be true taking log base b to the x, log base b of x equal to log base b of x and rewriting that as an exponential function. So if I were to rewrite this as an exponential function, my base would be b. Then the exponent would become the previous output, log base b of the x, and this would equal the previous input, x. So what these fundamental properties are basically a rewritten expression of a logarithm or a exponential function. Now, why this is important is what we can see here is if I have any exponential function that's b to the x power, so notice the variable x is in the exponent. If I take a logarithm with the same base, so there's my base of my exponent, there's my base of my logarithm. If I take the logarithm with the same base of that exponent, the result is just the exponent. So what this allows us to do is get exponents or get variables out of the exponent in order to solve. The same thing can be true if I have a logarithm. So if I have log base b of x, and notice again, x is the input variable of the logarithm. If I want to get x to be by itself out of that logarithm, I can use an exponential function with the same base as my logarithm. So let's take a look at some examples of this. In problem number 1, it says solve each of the following equations by applying fundamental properties. List an exact answer and an answer rounded to 2 decimals, and we'll do that only if needed. Sometimes we have just exact answers. So what we have here in problem number 1a is we have the natural log or log base e of x equal to 2. And we want to solve for this x value. And again, it's as if we had parentheses around the x. The x is our input of the natural log. So in order to get x by itself, think about solving equations. You want to isolate the x. We need to use an exponential equation with the same base as my logarithm. So remember, a natural log is log base e. So I'm going to take an exponential equation with base e. Now this expression, the natural log of x, becomes the exponent. Now if I enact this step on one side of the equation, I have to do the same thing on the other side. So e to the second power, I'd create this as an exponential function with e to the second power. So basically what I'm doing is I'm taking both expressions on either side of the equation and making an exponent of e. Again, we chose e here because that's the base of the natural log. So, according to the fundamental properties of logarithms, because the base of the exponent and the base of the logarithm are the same, they're going to undo each other. We know that's true because of exponential or inverse operations. And so what we get here is just x equals e to the second power. And so that is our solution for x. So we're able to get x out of the logarithm by applying the inverse operation of an exponential function. Now we can evaluate this expression Find a rounded answer for that by typing e to the second into the calculator. And so x would equal exactly e to the second power, which is approximately 7.39 rounded to the hundredth place. We can see another example of that in B. So in this case, we have another logarithm, and the x is the input of the logarithm. So what I need to do is I need to eliminate the logarithm to solve for x. So this logarithm, it's a common log, is of base 10. So I'm going to take log log x, the common log of x, and make that an exponent for base 10. If I do it to one side of the equation, I need to do the same thing to the other side of the equation. So I'm taking that negative 0.52 and making that the exponent of base 10. Again, I chose base 10 because that is the base of the logarithm. So on the right side of the equation, the 10 as the base of an exponent and log base 10 are going to undo each other's operations, leaving us with just x. So x in this case would equal exactly 10 to the negative 0.52 power, which we can go to the calculator and evaluate to get an estimated or rounded answer. So in this case, x would equal approximately 0.30. And if we're rounded to two decimals, we do want to include that 0 there. We're not rounding up to 1. We want to include that decimal, though, to show that we are rounding to the hundredths place. Taking a look at C, we now have an exponent or variable in the exponent. So what I need to do is get rid of the exponential equation here. Get rid of the base e. So with the fundamental property that we listed first, I'm going to use a logarithm with the same base. So logarithm base e is also written as the natural log. So I'm going to take this e to the x power and make that the input of the natural log. If I do that operation to one side of an equation, I need to do the exact same thing to the other side of the equation. So I would have the natural log of 167. On the left side, the natural log and an exponential function with base e are inverse operations, leaving us with just x. So x would equal the natural log of 167, which again, we can round into the calculator and get an estimated value of approximately 5.12. So this is one way that we can use, or one method of solving exponential or logarithmic equations. We can use the fundamental property of logarithms, knowing that logarithms and exponentials are with the same base are inverse operations of each other, which undo their operation, leaving us with just the input or the variable in this case. Now there are some other instances where we can advance this a little bit. So let's at this point go ahead and let you take a look at part D. Pause the video and see if you can complete part D. Hopefully you got an answer to D at this point. In part D, we see x is in the exponent of the exponential expression. So I need to use a logarithm with the same base. So a log base 10 is what we would be taking of both sides here. Log base 10 is the inverse operation of the exponential base 10. So because they're inverse operations, that's going to cancel each other out or eliminate each other, leaving you with log base 10 of 8.223. So this would be the exact answer for x, which can be evaluated in the calculator. And so our approximate answer would be 0.92. Now in E, we see an additional operation here, and it's going to give us an additional step. So when solving these, think about this as a reverse order of operations, or again, as we have called SADMAP. In order to deal with the exponent or the logarithm, I would be focusing on the exponent, the E portion of reverse order of operations. So before I get there, I need to isolate the logarithm or the exponential equation by doing subtraction or addition, followed by division or multiplication, before I even worry about the exponent. So in part 1E, in problem 1E, before I can deal with the 10 to the x power, I need to add 29 to both sides. So I need to move that 29 over by adding that to both sides. So I get 10 to the x power equal to 80. Now I can take the log base 10 of both sides, which would eliminate our exponential expression, leaving us with just x. So x would equal log base 10, or the common log, of 80. That can be evaluated in our calculator as approximately 1.9. The same thing must be considered in part F. So in F, I'm thinking again, reverse order of operations. I'm going to add 5 to both sides. So before I can get to the exponent here where my variable is, I need to eliminate or isolate that exponential expression. So I'm going to add 5 to both sides. Then I need to divide by 3 because that 3 is a coefficient to the exponential expression. So I need to eliminate that coefficient by dividing. Now I'm at a place where the exponential expression has been isolated. I can get rid of that exponential expression by using a logarithm with the same base. So a logarithm of base e is the natural log. At this point, what I get here is the logarithm and the exponential function eliminate each other. So I get x plus 1 equal to the natural log of 4. So I'm not done yet. What I need to do is subtract 1 from both sides. So I need to completely isolate the x. And so in order to do so, I need to subtract the 1 from x and the other side of the equation. So my exact answer here is going to be the natural log of 4 minus 1. So if there's expressions other than just the variable and the exponent, we have to continue our operations, our reverse order of operations, or SADMAP, once we get to that exponent to isolate the variable. So in this case, our exact answer is the natural log of 4 minus 1, and that would be approximately 0.39. Let's do one more example like this together. In this case, we see a logarithm in G. So before dealing with the logarithm, I need to get rid of the other pieces of the equation. So I'm going to subtract 1 from both sides. If I subtract 1 from both sides, I would get 2 times the logarithm of 7x, log base 10 of 7x equal to 3. Now I need to get rid of the 2, and I can do so by dividing both sides by 10, or by dividing both sides by 2, which has isolated my logarithm at this point. So this is log base 10. So I'm going to take an exponential equation with base 10 of each side. So the logarithm becomes an exponent of 10, and the 3/2 becomes an exponent of 10. On the left side of the equation, the logarithm and the exponential base will eliminate each other, leaving us with 7x equals 10 to the 3/2. From here, we need to isolate the x by dividing both sides by 7. So x is equal to 10 to the 3/2 power over 7. So this would be the exact answer, and there's not really any way to simplify that expression, but we can find a rounded version of that expression in the calculator by computing that expression to get approximately 4.52. So what we can see here is that this follows basically the same steps of solving any other equation with reverse order of operations, other than the point where we get to the exponential equation or the logarithm expression. In such case, we have to use the inverse operation to eliminate that exponential expression or logarithmic expression. So go ahead and pause the video and see if you can complete 1H. Hopefully you got an answer to problem 1H, and so let's work through these steps together. So we need to get rid of this logarithmic expression in order to solve. So we're going to follow reverse order of operations, and in this case, add 5 to both sides first. Then we can divide both sides by the coefficient, -4. And now we're in a location where we can eliminate the natural log. So to eliminate the natural log, we have to use the exponent with the same base. And the base of a natural log is e. So I'm going to have e to the exponent of natural log of x plus 1 on one side and e to the negative third on the other side. On the left side, the exponent and natural log eliminate each other, leaving us with just x plus 1, and then I can subtract 1. So x is equal to e to the negative third power minus 1. We can then compute that exact answer in the calculator. So e to the negative third power minus 1 is going to be approximately negative 0.95. So these are examples of how we can use the basic or fundamental property of logarithms in order to solve logarithmic and exponential equations. This is a good place to stop for now. Thank you guys for tuning in, and as always, I'll see you soon.